Hello friends, welcome to my lecture on applications to the problems of potential flow. The Laplace equation del square u equal to 0 is one of the most important partial differential equations in engineering mathematics because it occurs in connection with gravitational fields, electrostatic fields, steady state heat conduction, incompressible fluid flow, etc. The theory of solutions of the Laplace equation is called the potential theory. Now, in the two dimensional case, the Laplace equation del square u equal to 0 becomes uxx plus uyy equal to 0. We shall see that its solutions are closely related to complex analytic functions. When we will look at the solution of two dimensional Laplace equation, we are going to see that they are closely related to complex analytic functions. Let us first discuss Coulomb's law. Let R be the distance between 2 point electric charges Q1 and Q2. Let us say 2 point electric charges Q1 and Q2. Okay. Then the force of attraction and repulsion between them is given in magnitude by F equal to Q1 Q2 over K R square. Here K is the dielectric constant and it depends on the medium. In a vacuum, the value of K is 1 and in other cases the value of K is greater than 1. Now, let us consider a discrete or continuous or a combination of both charge distribution. This charge distribution sets up an electric field if a unit positive charge is small enough so as to not affect the field appreciably is placed at any point A not already occupied by charge, then the force acting on this charge is called the electric field intensity at A and is denoted by this symbol. Okay. This force is derivable from a potential phi which is called the electrostatic potential. Okay. And we have this, we can call it as big epsilon is equal to minus del phi. Okay. If the charge distribution is two dimensional, then this big epsilon is Ex plus I Ey. Okay. And this big epsilon is minus del phi. So, this is equal to minus phi x minus I phi y. When we write the this is the notation in the complex plane. Okay. As such, del phi is I phi x plus j phi y in two dimensions. But when we write its corresponding representation in the complex, okay, it will be written as minus phi x minus I phi y. So, we have minus phi x minus I phi y, and here also you can see this force epsilon is written as Ex plus I Ey. This is the complex representation of the field intensity, which is Exi plus Eyj. Okay. This iota is a complex number, this iota is not the unit vector. Okay. This iota is here, this iota is square root minus 1. Okay. So, Ex is equal to then minus phi x and Ey equal to minus phi y. Now, it follows that in any region free of charge, the partial derivatives of Ex plus partial derivative of Ey, that is equal to 0. Now, Ex is equal to, we have seen Ex is equal to minus phi x and Ey is equal to minus phi y. Okay. So, Exx is equal to minus phi xx and Eyy is equal to minus phi yy, which implies that we have the partial derivative of Ex with respect to x plus partial derivative of Ey with respect to y. Okay. This is what we have. Okay. So, since we have partial derivative of Ex with respect to x plus partial derivative of Ey with respect to y is 0, we have phi xx plus phi yy equal to 0. Okay, which means that phi is a harmonic function. At all points which are not occupied by a charge. Now, we have a harmonic function phi with us, okay. So, we can find its corresponding conjugate harmonic function psi, okay, such that the complex function omega z is equal to phi x y plus I psi x y. Phi x y is the real part of omega z and psi x y is the imaginary part of omega z. Now, this function is analytic in any region not occupied by the charge. The function omega z is called the complex electrostatic potential. Okay. This function is called the complex electrostatic potential. The curve phi x y equal to alpha, okay, and psi x y equal to beta define two level curves, family of level curves. Okay. Since phi is the potential, okay, we are writing this big epsilon as minus del phi. So, that is the phi is the potential there. So, phi x y equal to alpha means the curves phi x y equal to alpha, the level curves phi x y equal to alpha are called as equipotential lines, or you can call them as equipotential curves, because on every curve the potential is the same, and then psi x y equal to beta are known as the lines of force, okay, respectively. Lines, we write lines, but they can be called as curves. So, the lines of force cut the, now we have seen that the family of level curves phi x y equal to alpha and psi x y equal to beta, they cut each other orthogonally, okay. So, the lines of force cut the equipotential lines orthogonally. Note that psi x, why we call psi x y equal to beta as lines of force, because psi x y equal to beta, the direction of the electrical force, okay, we had the electrical force minus del phi, okay, and this del phi is a vector which is perpendicular to phi x y. We know this, that del phi is a vector perpendicular to phi x y equal to constant, okay. So, del phi is a vector perpendicular to phi x y, and psi x y equal to beta is also perpendicular to this phi x y. Therefore, the direction of psi x y equal to beta and the vector electrical force, this electrical force are same, and therefore, we call psi x y equal to beta as lines of force. So, let us note that psi x y equal to beta are called the lines of force, because the electrical force which is minus del phi, it acts in a direction perpendicular to the equipotential lines phi x y equal to alpha, okay, that is along the lines psi x y equal to beta. Now, let us consider two parallel conducting plates. One conducting plate is this one, the other conducting plate is this one. They are extending to infinity, and they are capped at potentials u1 and u2. So, this is having potential u1 throughout, and this is having potential u2 throughout, and they are infinitely long. Then from the shape of the float, shape of the plates, it follows that u depends only on x. You can see that u is constant on this plate, okay, it does not depend on y, it is equal to u1, okay, throughout this plate, and this is, let us say this plate is x equal to this plate is parallel to y-axis. So, the equation of this plate is x equal to some constant, okay, and so for all values of y, you can see u is equal to, if u denotes the potential, then u is equal to u1, and similarly here this is this plate is given by another equation x equal to some constant, okay. So, along this plate also for all values of y, okay, we have u equal to u2. So, u depends only on x, it does not depend on y, okay. So, since u depends only on x, the Laplace equation del square u equal to 0 gives us u x x equal to 0. Del square u is u x x plus u y y equal to 0, okay. This implies that u x x equal to 0, because u is independent of y, okay. Now, u x x equal to 0 is when we integrate it twice. If you integrate it once, what you get? U x equal to some constant, say a, okay, and when you integrate it again with respect to x, you get u x equal to a x plus b. So, u is a function of x, it is linear function ax plus b. Now let us use the condition that when x is equal to we have the condition that and on this plate u is equal to u1, on this plate u is equal to u2. So, when we use that we get the values of a and b. Okay. So, let us put them as x equal to 1 and minus 1. So, this is x equal to minus 1, okay, and this is x equal to 1. Okay. So, when you take x equal to minus 1, x equal to 1, what you get? Ux equal to u1. So, u1 equal to minus a plus b. Okay. u1 is minus a plus b and u2 is equal to a plus b. Okay. So, when you add the two equations u1 plus b, get u1, adding these, let us call it as 1 and this as 2. So, then 1 plus 2 gives you u1 plus u2 by 2 equal to b. Okay. We get the value of u1 plus value of b as u1 plus u2 by 2, and when we subtract the equation 1 from 2, so 2 minus 1 gives you what? u2 minus u1 is equal to 2a. So, that gives you a equal to u2 minus u1 by 2. Okay. So, we get the values of a and b by taking the two plates at left plate at x equal to minus 1 and the other plate at x equal to 1. Okay. We get the values of a and b, and then putting the values of a and b, then ux is equal to 1 by 2 minus u1 plus u2 into x, 1 by 2 u1 plus u2. Okay. Now, ux is potential. Okay. Ux is potential. So, if you take potential to be constant, then you see that ux equal to constant gives ux equal to constant gives minus 1 by 2 u1 u2 minus u1, 1 by 2 u2 minus u1 into x plus 1 by 2 u1 plus u2 equal to constant. Okay. Since u1 plus u2 by 2 is a constant, u2 minus u1 by 2 is a constant, this implies that x is equal to some constant c. Okay. Some constant c. Okay. So, when we take ux by ux equal to some constant, we get x equal to some constant. So, means for different values of the constant we will get different lines which are parallel to y-axis. So, equipotential lines are surface lines, equipotential surfaces are parallel lines, they are parallel to y-axis. If bxy is the conjugate harmonic function of uxy, then we can find the value of bxy by using Cauchy-Riemann equations. We have uxy equal to, we have ux, u is not depending on y. So, ux equal to ax plus b we have, where a is equal to u2 minus u1 by 2, b is equal to u1 plus u2 by 2. Okay. Now, let us use the Cauchy-Riemann equations. So, ux is equal to by and uy equal to minus bx. So, let us first use this equation. So, uxb is equal to a. Okay. So, a is equal to by. So, this implies b is equal to ay plus some constant, let us say some constant of integration which will be a function of x. So, let us write Cx. Okay. Now, we will make use of this equation to determine this unknown function of x. Okay. So, this gives you, let us differentiate this with respect to x. So, derivative of b with respect to x gives you y is independent of x. So, this will give you c dash x. Okay. But from here this bx is equal to minus uy. So, this is equal to minus times uy is how much? Uy is 0. Okay. U is not depending on y. So, this implies C dash x is equal to 0, and which implies C x is a constant. Okay. It is a constant. I have denoted this C x by C. Okay. So, that is C x is some constant C. Okay. So, what do we get by B equal to A y plus C, where A is this u2 minus u1 by 2. Okay. So, B x y equal to this one 1 by 2 u2 minus u1 into y plus C, and now let us find the complex potential, because we have u and y with us. So, omega z equal to u x y plus I b x y, u x y is equal to A x plus b. So, see omega z equal to u x y is A x plus b plus I times b x y is this is A. Okay. So, A y plus C. So, what do we get? A times x plus I y plus b plus I into C. Now, this is A z plus b plus I c. Okay. So, this is A z plus b plus I c. A is u2 minus u1 by 2 and b is u1 plus u2 by 2. C is a real constant. The lines of force are, now what are the lines of force? Lines of force are given by u x y equal to constant gave us the equipotential lines, b x y equal to constant gives us the lines of force. So, b x y equal to constant means b x y equal to constant implies A y plus C equal to constant. Okay. Now, C is a constant, A is a constant. So, this implies y is equal to constant. Okay. So, the lines of force are parallel to x axis. Okay. So, lines of force are parallel to x axis, the equipotential lines are parallel to y axis. So, they cut each other at right angles, they define two orthogonal families. Now, let us consider two conducting coaxial cylinders. So, we have two coaxial cylinders, they have the same axis, okay, they are coaxial, which extend to infinity on both sides. Okay. So, on both sides of the axis they are extending to infinity and are kept at potentials u1 and u2 respectively. So, let us say this is u1, okay, this is u1, this is u2, okay, they are kept at potentials u1 and u2 respectively. So, here what is happening is that the potential u, okay, at any point is given by, at any, let us say at this point, okay, it is given by the distance of this point from the origin. Okay. Let us say the distance of this point from origin is r, then here u is a function of r. Okay. We have the two conducting coaxial cylinders which are kept at potentials u1 and 2. So, that means that on the coaxial cylinders the constant the potential remains constant. So, potential varies when r varies. Okay. U is a function only of r. So, u is a function of r and r, where r is equal to under root x square plus y square. Okay. Now, let us see what is f r, what is the value of f r. Okay. So, u is a harmonic function of r. We can see that since u does not depend on theta, okay, we have u equal to u x x plus u y y equal to 0. So, let us recall the Laplace equation in polar coordinates. It is u r r plus 1 by r u r plus 1 by r square u theta theta equal to 0. Now, since u is independent of theta, okay, since u does not depend on theta, u theta theta equal to 0. Okay. Thus, u r r plus 1 by r u r equal to 0. Okay. Now let us find URR. So URR is equal to UR equal to F dash R, okay, and URR is equal to F double dash R. So what do we get? F double dash R plus 1 by R F dash R equal to 0, and this gives us F double dash R divided by F dash R equal to minus 1 by R. Okay. So ln F dash, so let us integrate with respect to R. So ln F dash R equal to minus ln R plus some constant, let us say ln C. Okay. So then F dash R equal to C by R. Okay. Now this integrate, when we integrate it again with respect to R, we get F R equal to C ln R plus some constant D. R, you can say, if you replace the constant C D by A and B, you get F R equal to A ln R plus B. A and B can be determined by the given values of U on the two cylinders. Okay. So U equal to A ln R plus B, and R can also be written as mod of Z. Okay. So in complex we can write U as A ln mod of Z plus B. Now B, let us say that B is the conjugate harmonic function of U. Okay. Then what will happen? U is equal to constant means ln R is constant, means R is constant. R is constant means C, if U is constant, then A ln R plus B is equal to constant. Okay. A and B are constants. Okay. A ln R plus B equal to constant means ln R is constant, and which implies that R is constant. Okay. So R is constant means what? The equipotential curves. U is a potential. Okay. So equipotential curves are concentric circles with center at 0 0. R equal to constant means it defines a circle with center at 0 0, and Bxy equal to constant. Bxy is what? Bxy. Okay. Let us find Vxy. Vxy we can find by using the Cauchy-Riemann equations in polar form. Cauchy-Riemann equations in polar form are UR equal to 1 by R B theta. So using Cauchy-Riemann equations, UR equal to 1 by R B theta, what do we get? UR is equal to, we have found FR. FR is equal to A ln R plus B. So U equal to A ln R plus B gives partial derivative of U with respect to R, UR equal to A by R. Okay. Okay. So CR equations in polar form are UR equal to 1 by R B theta, U theta equal to minus R B R. Okay. Now U is equal to A ln R plus B. So UR is equal to A by R. So A by R equal to 1 by R B theta. First equation gives us this, which implies that B theta equal to A, and when we integrate with respect to theta, what we get? B equal to A theta plus some function of R. I can write that as phi R. Now here U theta equal to 0 because U does not depend on theta. So this second equation gives us 0 equal to minus R B R, which implies that B R equal to 0. Okay. And this means that when you differentiate this B with respect to R, what do we get? B equal to A theta plus phi R when we differentiate with respect to R. So we have this, theta is independent of R, so we get phi dash R, but this is equal to 0. Let us use this. So this is equal to 0 implies phi R equal to arbitrary constant, say C. Okay. So what do we get then? Okay. Hence B equal to, let us recall this, B equal to A theta plus some arbitrary constant C. So if Bxy is equal to constant, okay, Bxy equal to constant means A theta plus C equal to constant, and this will imply that theta equal to constant. Okay. So, the lines of force are straight lines which pass through 0 0, okay, because theta is constant. So, you can see the lines of force are passing through origin, okay, and equipotential curves are concentric circles with center at origin. So, at the point of intersection they are they cut each other at right angles. With this I would like to end my lecture. Thank you very much for your attention.